So as far as the first law of thermodynamics go, we are looking at a closed system. So first is closed system. And the other thing is that as far as if you have a closed system, this is actually the heat input. So you actually put in heat into the closed system, and we expect the two things that will happen. Whatever gas is inside will now actually gain total internal energy, and that is actually reflected here. So if you have a heat input, your total internal energy will actually increase. So increase the internal energy. And aside to that, if there's this in this closed system, there's actually a piston, then what would actually happen is that the as the gas gains heat energy, they will try and expand. Okay, so if there's a piston, then you will find that you will get work done in this case by the system. Very important. It's not on the system. Okay, so this is actually the formula that explains that. Quite clearly, we could actually now take a look at the what happens if, let's say, heat is now being removed. So in the same vein, if heat is removed, the change in Q in fact is less than 0. All right, and the internal energy will drop as well. So change in U will also be less than 0. And the other possibility is that now, because your heat energy is being removed, your piston may start shrinking. Okay, and in those circumstances itself, you will find that you will have work done on the system now. On the system means you're actually compressing. So in this case, when it's work done on the system, based on this is actually 0. Maybe the last part that I just want to add on is to say that why, when you start learning this formula for the first law of thermodynamics, it is best to learn it in this form, because we probably remember that there's another form that is this. Obviously in the exam, if they give you this, then you have to follow the convention. In this case now, this means that work done on the system is positive. All right, so it's the opposite. So work done on the system is positive. While in this, if you were to decide to use this equation, then work done by the system is positive. If it's work done on the system, you got to make sure it's negative. Okay, which makes a lot of sense, because if, let's say, this is if work is done on the system, that means this number become negative. Technically, when you move it across down here, the equation changes to this. That's the reason why in this equation, when it's stated, they define the change in W as work done on the system. Final part to add on is to explain that why we prefer this convention, this expression, rather than to use this for exam. The reason is because when you are actually calculating your change in work done, okay, it is typically you have a pressure, you will multiply by the final volume multiplied by initial volume. By selecting this convention, it is very clear-cut, because if you are expanding, if the gas is expanding, then it's work done by the system. So this naturally will be positive. So let me say that if it's work done by the system, we expect there to be expansion, correct? So if there's expansion, then your value of your final volume vis-a-vis your initial volume, your final volume will definitely be higher than that. So end up your change in W is actually positive. The problem with using this convention is that you must actively remind yourself that when you calculate the change in W, all right, you are in actual fact taking the initial volume subtract by the final. So this kind of like go against the grain of what you typically would do. So which is the reason why normally when we teach, it is proposed that we stick to this convention for calculations as much as possible. Only if the exam questions give you this convention, then you have to stick to that. Let's take a look at the application of this thermodynamic first law on the first process we call isobaric. So in isobaric process, if you look at actually the PV graph, then you find that the pressure is constant. You can see down here that the pressure will be P0. So this is the initial volume. This is the final volume. So in this questions itself, you will find that what we could do is first to tell ourselves that for this to happen, if you were to remember based on if you were to draw there's actually a line called the isotherm line, all right? That means let me recap first. If you can remember, you plot PV equal nRT graph, then you do get lines as such, whereby respectively the temperature is getting higher. Correct? Because as the temperature goes up, the graph will start shifting on. Okay? So based on this, it should be quite clear to you that in terms of the process, the isobaric process that moved from point 1 to point 2, the temperature would have increased from T1 to T2. Okay? So the conclusions of, the application of the equation itself now looks as such. That means there's still a heat input, the temperature does increase, and now there's also a work done by the gases actually, and your change in W is actually calculated as such. Okay, now let's take a look at the next process, isothermal process. In isothermal process, the temperature will remains the same. So under those circumstances, if your temperature did not change, then if you recall, the change in U will actually now be 0, because the internal energy, the total internal energy of an ideal gas is 3/2 nRT. Because your change in T is 0, your change in U is 0. Okay, so that is a key characteristic you need to remember for isothermal process, which means in this case, you will find that the heat input is now only used for expansion. So the area under this graph here, okay, this area will actually now be the work done. So your work done will be the area under the graph, and more importantly, we all know that as far as change in U is concerned, it is 0. So the change in U goes away. We cancel it because it's a 0 value. Next process to look at is isochoric process. Isochoric process typically have a case whereby the pressure will change, but the volume will not. So it could be from point 1 to point 2. So exactly the same volume. So in this case, if you have to calculate based on the work done by the system itself, it will actually be 0, since change in V is equal to 0. Is it alright? So in this case, this will be cancelled away, this will be 0. In this process, for discussion, when 1 goes to 2, actually, all right, if this is actually the respective isotherm line, all right, then you will find that if this is T1, this is T2, actually the temperature drop in this case. So it means that in the exam, they may be asking that in the process 1 to 2, we know if the temperature drops, the internal energy becomes negative. If it becomes negative, then your change in input also becomes negative, which simply means that heat energy is now given up. So heat energy is given up to the environment. Final process that we look at is the adiabatic process. There's actually 2 possibilities. There's an adiabatic expansion, which means that the volume expands from this to this. Temperature is T2 here and T1 here. So in this case, obviously T1 is larger than T2. Adiabatic process, the key characteristic is that the whole entire container is insulated. So it means that your change in heat, they doesn't allow any heat to be transferred into the system or out of the system. So your change in Q, in this case, is 0. Which means if you were to look at the expression, you will find that that means that your change in U is equal to minus change in W. All right. Okay. So as evident in these questions here, you can see that your change in U drop. So therefore, in the process of 1 to 2, this change in U is now less than 0. Okay. Because the temperature actually decreases from T1 to T2. T2 is of a lower temperature, which means that the as far as change in W is concerned, so if your change in U is less than 0, from this expression, we can say change in W is more than 0. So you can clearly see that in this case, your volume still expands. All right. In the case of this will be called as an adiabatic expansion. So in adiabatic expansion, the temperature of the gas drop. Conversely, we can now look at the opposite of that, which is actually we're going to look at contraction. So in the case of contraction, this is the way that you will go. So now T1, this is T2, all right? T1 still larger than T2, okay? Okay, so in the case of adiabatic contraction, you will find now the temperature actually increase, okay? And quite clearly what you get is actually compression. Unlike here, this is actually an expansion, all right? So in the case of a contraction, we know that the change in V is less than 0. Because your change in V is now less than 0, your change in W, okay, will also be less than 0. So negative change in W will now be a positive value. So implying, so therefore your change in U is more than 0. Okay, and so in adiabatic contraction, all right, you will find that what happens is that the temperature of the gas actually increase. Okay, now we take a look at the final process. It's actually called a cyclic process, which means that you will always have a start state, and then whatever processes you undertake, eventually you still go back to where it first started. So we have worked out two possibilities. One is when it is clockwise and it return back. The other one is when it's anti-clockwise. So before I start, if you look at cyclic process, the key characteristic is that because if start state is at 0.1 and it ends with also 0.1, it means that the change in U will be 0 because the temperature will eventually has not changed. Hence, if change in U is 0, by looking at this expression, then quite clearly your heat input should be equal to the work done by the system. All right. So bear in mind that when you have cyclic process, this is actually the equation that we'll be looking at. And by looking at the two possibilities, one whereby the cyclic process is clockwise, the other one anti-clockwise, you will find that the one that is clockwise, basically the amount of energy or the amount of work done, the total amount of work done by one cycle would in this case be positive, because the work done by 2 to 3 would actually be the area under the graph. 4 to 1, in actual fact, it's actually a smaller area. All right. Hence, because of this, when the process goes in the clockwise direction, there is work done by the system because your change in W is more than 0. Since your change in W is more than 0, it's a positive number, the change in Q will also be a positive number, which means that heat goes in to allow or to enable work done by the system. Basically, in this cyclic process that we're studying, it is actually mirroring that of an engine. So in the engine, you burn fuel to actually provide the heat energy, and the gas in the cylinder could now do work, all right? Could be expanding, all right? Okay, so this process mirrors that of the engine. So now if you look at the anti-clockwise, it's different because now in this case, clearly the process 3 to 4 has a larger area now, so that's contraction. Hence, your work done will be negative value, all right? So if your work done is negative value, it means that there's work done on the system now. It means you're compressing the gas, okay? So the compressing itself would have resulted the fact that your change in Q will be less than 0. Since change in W is less than 0, change in Q is less than 0, which means heat energy is now given out to the environment, all right? So this mirrors that of the performance of a heat pump, because you can now be compressing, all right, the gases, and the gases actually release heat energy to the environment.